And one of the wonderful things I found out that there is very little pushback on the idea of introducing engineering into science education. Because, well, I've been doing this for a long time now, probably about 10 years, really. I'm a retreaded science teacher. Science has always been my area, but I never made a distinction between science and engineering. And when I realized that there are some differences, because I worked with some engineers, I realized that we need to teach both of them intentionally, and that there are real differences between the two. So, but then I encountered a lot of people who said, engineering, look, we don't have enough money or time or materials to teach science. You're also going to ask us to teach engineering? I'm not an engineer. I don't know how to do this. But in fact, it's not a big stretch, and often what probably many of you in the room are already doing that. It's a matter, in my view, of marrying the science and the engineering. And that's what today's talk is all about, is how to go about that marriage. So, and I will mention initially that there are a lot of activities that teachers do that are just engineering. So, for example, building a bridge and testing it to failure, building a tall tower and seeing where it fails, the egg drop, the famous egg drop activity. Those are all engineering activities, engineering design. Some of them better than others in the sense that if you focus on failure modes, if you look at trade-offs, criterion constraints, it becomes more specifically the concepts of engineering and the principles of engineering. But if science is not also a part of it, if you don't introduce Newton's laws of inertia and, or all three laws, whichever law happens to be appropriate for the given activity, then in my view it doesn't belong in the science classroom. But how to do it is hard. So that's what we're going to talk about today. So we're going to do three things, actually. We will spend the last part of the activity talking about engineering the future. I directed that project. Many people worked on it. Dozens of teachers and thousands of students, actually, helped with that. So I will talk about that as a curriculum, and it is published by It's About Time. This is an exhibitor workshop. So I promised to talk about that. But first, I'm going to talk about some broader issues of how we deal with this idea of engineering in the curriculum. I've been thinking about this for a long time. I've had some wonderful, challenging questions, and you'll hear a little bit about that in a few minutes. So, so we're going to begin with a new publication by the National Academy of Sciences. Let me advance this a slide. Okay. There's a new guide, and if you Google Guide to Implementing the Next Generation Science Standards, you might have to add NAS, National Academy of Sciences, or NAP, National Academy of Press, in the beginning of that if you have any difficulty. I just Googled this title, and it comes up. You don't even have to go to the download site. There it is. You just click through it. And I was on a small committee by the National Academy to provide guidance for what we do during this transition period, because it really is a transition period from where we've been to where we'll need to go. Now, I realize not all states are adopting the NGSS, but many states who are not going to adopt because they can't possibly do that for political reasons or other reasons are nonetheless using the NGSS as a way to think about their own standards. And more states, even those who are non-NGSS adopters, are including engineering for a number of good reasons. It's much more motivating for kids in many ways. It's a lot easier to help kids understand the value of science and math. It's a glue that holds the different STEM fields together. And it's a practical skill because, in my view, everybody in life needs to know how to solve problems. And it provides a structure, a set of guidelines for doing that. And, of course, developing the curriculum is an engineering task in itself. So we try to apply some of those principles in doing that. So let me move on a little bit to what this guide has to say about curriculum. And it makes these 4 recommendations. First of all, don't rush to replace your curriculum at present. Really get familiar with the NGSS or your state's standards and know what you're looking for. Second, decide on the course scope and sequence. So decide what you want to teach before you get the materials, rather than getting the materials and having that tell you what to teach. The third one is be critical consumers of curriculum materials. Now, yesterday I did a presentation actually applying the Equip rubric to the PBIS middle school curriculum. I don't know if some of you were there or not. It's a tedious process, really stepping through it. We're not going to do that today. I'm going to kind of give you broad brushstrokes today. But it's a lot of work to do that. You got to do it. But if you're going to spend that time on one set of curriculum materials, it could be a couple of days of time. Hopefully, your principal is paying you during the summer to do this if you're on one of these curriculum committees. Which one do you choose? Which ones do you spend that time with? I'm going to answer the question in a minute. And I'm not just going to tell you the answer. I'm going to tell you how to find the answer, because your answers may be different. The last one is attending to coherence in the curriculum. It's not just a question of whether or not the curriculum is aligned to the NGSS. But is it coherent? Does it make sense? Does it go from here to there? Is it coherent from grade to grade in terms of where the kids in your school are going to go? You really have to think about the whole curriculum and the pathway that you want your kids to take. Now, one of the pathways to consider, and this is new, is to start with engineering in freshman or 9th grade. And it does something different. It helps the kids say, oh, I might want to go into this field. It's kind of interesting. Besides, there are 4 jobs in engineering for every job in science. You know, we're used to teaching our kids, you can be a scientist. Well, you can also be an engineer. And if you're an engineer, you can actually get a job. So NASA hires 9 engineers for every scientist. When you think about it, it's not surprising because, you know, NASA folks have to design rockets to go up into space. Spacecraft, that's engineering. And sure, scientists do research on that, and it takes science to do some of the problem solving about life in space and propulsion systems and so forth. But most of the work is actually engineering, figuring out how to accomplish a goal. And that's the big difference. In science, it's all about answering questions about the natural world or the design world. If you're really after the truth, that's science. If you're trying to make something work, that's engineering. You got to have both. That's why I think they both belong in the science classroom. So let me go forward a little bit. And the first thing I'm going to do is quickly go through what does engineering look like in the NGSS. Now, many of you may have already looked at that. I'm just going to give you a quick overview and a reminder, and in particular tell you some of the puzzles to solve and a couple thoughts about it. Then I'm going to show you a resource to help you decide which curricula to spend time with. It's published by a different publisher, not by It's About Time. It's published by Corwin Press. And I'll tell you why a little bit later they let me talk about it here. I did get it cleared. But there's a reason for that. And I'll get to that in a few minutes. And then finally, I'll talk about this particular curriculum, Engineering the Future. But it is just one of a dozen that you want to look at the high school level. So let me go through this. So first of all, in the NGSS, engineering is a core idea, just like Newton's laws. Secondly, it's a practice. We want kids to be able to design things, to solve problems. Thirdly, it's a cross-cutting concept. Part of it is a cross-cutting concept, in particular the idea that engineering and science are a two-way street. Each one helps the other advance. And fourth, it's embedded in all the other disciplines. So if you look at any of the other disciplines, you'll find design this, use computational thinking to do that. Even the performance expectations that don't involve engineering specifically, you don't just apply one practice when you're developing a unit. And if you include engineering activities in the unit, you help, pardon me, you help the kids understand the science concept better. So it really is embedded in all of the other instructional, in all of the other classes. In any given activity or lesson, engineering might be first, or science might be first. It doesn't matter. And in many cases, it depends. I personally like to begin with a goal. Why are we doing this? Because I had two kids. They were 6th graders. I started in high school. I worked my way up to middle school. And I found these two kids always challenging me every time I'd introduce a class and new topic. They'd say, Mr. Sneider, why are we doing this? So I had to have a reason that made sense to them. And if the reason had to do with something that was really important in the world, it made a lot more sense than, because this is a neat idea. You know, it was a little hard. My favorite subject was always astronomy. It's really hard to explain to kids why black holes are important for them to know about. I mean, I found ways, you know. but engineering is actually a lot easier to make sense to them. And there are so many contexts and scenarios and problems to solve in the world. Fundamental ones, like public health, like environmental change. Ecosystem is full of problems to solve when teaching life sciences. To say nothing of enough fresh water and food to grow a population that's going to grow from 7 billion today to 9 billion by 2050. Our kids are going to have to solve these problems. And it gets their attention. It really does. So let me go on with, and I'm going to go through these rather quickly to spend a little more time. Engineering design is a practice, and I just love this particular picture because this girl invented a technology for blowing bubbles. You put your fingers together, makes a little loop, and then you blow the bubble, and this kid next to her who'd been spending a lot of time with his little plastic stick there trying, he said, wow, how did she do that? So anyway, it's, you don't need a lot of expensive equipment to do engineering design. You need good questions and good problems to solve and good facilitation. It takes good teachers. Materials, by the way, will never do it. It takes good teachers. Materials can help teachers do a good job, but it takes good teaching. So quickly to go through these practices. Now this is engineering design as a practice. And so the first one, in science, you start with a question. In engineering design, you start with a problem. In this way, engineering and science are very different. But in most other ways, the practice is really similar. The goal is what makes the difference. So in the second one is developing and using models. Scientists will develop a model of, say, a honeybee and a flower and try to figure out with a particular flower, how does this honeybee pollinate this particular flower. You've got a mental model of it. You may make a working model. So the engineering's elementary curriculum has kids actually make little mock honeybees and see how a honeybee actually pollinates a flower. So scientists often develop models to better understand something, to represent how they think they understand it. Astronomers do this all the time because you can't actually experiment with galaxies, but you can build mathematical models and use computer simulations and so forth. But engineers use models for a different purpose. Their purpose is this design going to work? Or their purpose might be to try to understand the system so they can find out the problems with it. But they both use models. And a model, again, is something kids need to understand. It represents certain aspects of the world, but not the whole world. If it did, we wouldn't be able to use it. I mean, you might as well use the real world. So a model specifically, there are certain things about when you use a model, how to use a model. Same in science or engineering, it's just the goal that's different. So the next one is planning and carrying out investigations. This is what we always used to emphasize in science, how to do a controlled experiment. And again, in science, you do it to understand, you test your hypotheses. In engineering, you test your model to see if it actually works. Sometimes in engineering, testing a model means taking it out to the people who are actually going to use it and say, would you use this? That's a test. But then you've got to use that information to revise what you're doing, or it really isn't engineering. And that part of it is the analyzing the data, and then you have to interpret the data. Sometimes data is numerical data with independent and dependent variables. Sometimes that data is what somebody told you about what they think about what you did. And often using mathematics and computational thinking. There's a difference between these, and I've got 3 articles, one in the Science Teacher, Science Scope, and Science in Children in the last year, about the difference between mathematical and computational thinking. And computational thinking involves using algorithms and using the capability of a computer, not just to do probeware, but in all sorts of ways. So that's one way, is to use algorithms to solve problems that would be otherwise too tedious to solve. But computers today also provide incredible collections of data, and just mining data is another way of using a computer. So thinking about these two, that's kind of the next frontier in my view in science education, is how to really get kids to think. And in terms of computational thinking, what can computers and other digital assistants really do? So here's the other area in which they're really different. So in science, you've got a question. Now you want to explain the phenomenon. That's the goal. So a cancer researcher wants to understand how a tiny tumor in one part of the body metastasizes to the rest of the body. They are doing fundamental research. How does this get from here to there? That's absolutely critical to developing a cure. You need to know how it works. Medical engineering is then taking that knowledge and applying it to treatments. What do we actually do to help people? You need to have both. You really do. So designing a solution is kind of the counterpart. It's a different task, but it's the counterpart to finding an explanation in science. It's kind of the way they work together. It's listed as a practice of science and engineering, but it's really 2 different practices that are related. And the next one is engaging in argument from evidence. And this one is emphasized much, much more in the new framework than it used to be. And the idea is that it's not enough to do the experiment, because everybody, not just kids, all of us, we like to find the data that supports our view. It's a human thing to do, to cherry pick the data, all right? What happens when we say, okay, let's lay down the evidence, let's look at our claim, and let's look at the argument that goes from the evidence to the claim, and then let's rebut it, and let's rebut each other's arguments. And you look not only at the evidence, but also at that rationale that connects the evidence to the claim. You can also ask, is this the right evidence? Is this the only evidence? Do we have the right evidence? And how good is our argument that goes from the evidence? It's called a warrant, is that rationale. So thinking about how to think, that reflection is really important, and we're going to get to that in just a minute. And then finally, obtaining, evaluating, and communicating information. You know, let's not disparage the activity where you send the kids to the internet to do a little research that night, because scientists and engineers do that all the time. And you'll find in the Common Core standards that's what's really important too, that learning to read technical information. And we need to teach students how to do that. There's a couple of really good books that I saw recently about how to do that. There's a lot of literature on that too. And okay, so that brings us to engineering as a core idea. And this is my colleague, Yvonne Spicer at the Museum of Science in Boston, and she's helped me a lot with this. She's from the CTE field, Career and Technical Education field. And really, career and technical education is really coming together with science education, informing each other. And I recommend those partnerships whenever possible, because frankly, the CTE teachers and the technology teachers have the capabilities to help kids realize their designs. And I'm so sad when schools eliminate the shop. So these are the 12 core ideas in the NGSS. They aren't actually emphasized because we have the performance expectations emphasized. They are emphasized in the framework. And there are just 12 of them. So Earth's place in the universe ecosystems, heredity, waves, energy, forces, engineering design. All at the same level, they're all really important. Now, Esther Hopkins is here, and 2 years ago, I think it was, when I was working on the NGSS, and we had had a public release of the information, Esther said, I don't understand this. How can you have engineering design both as a core idea and as a practice? But you don't do that for science. In science, you have science as a practice, but you don't specifically have the nature of science as a core idea. Now we do, to some extent, we have it as a cross-cutting concept. So nature of science is back in there. We want kids to understand nature of science explicitly. The difference between a practice and a core idea. Practice is what we want kids to be able to do. They could do it without knowing they're doing it. The core idea means they know what they're doing. They are explicitly aware that in engineering design, you start with a problem and you have to define the problem in terms of criteria and constraints. That's from 3rd grade and above. Younger children, the idea is something's worrying you, you don't like it, you got a system you want to change. That's a problem that we can solve. It's an orientation, an attitude, and an ability to start doing something. Starting with 3rd grade and above, you actually have specific criteria for success and constraints. And as kids get older, they learn ways of systematically solving those problems. So there's a progression of ideas of engineering design. So it's really important. Now, I'm going to answer the question that everybody has asked me, and I'm just telling you this is my own opinion. How do you teach it as a core idea in science? And does that mean you just have these classes where you're dropping eggs and building bridges and you don't talk about the science? Absolutely not, in my personal view. What you do is you make sure that every activity that is focused on engineering, that is primarily about engineering, and helping those kids understand those core ideas, also involves some science. So, for example, dropping the egg. Why doesn't the egg crack? Why does the egg crack when you have nothing to protect it? What does the protection do? Start with those open-ended questions. Remember, we talked about forces. We talked about energy. What's happening with this egg? Start with some open-ended questions. Go with some more focused questions, all right? In order so the energy doesn't go all into that egg, what do we have to do? Now, the egg has this kinetic energy, right? It's accelerating. When it hits the floor, it has that energy. It has to come to a stop. Regardless of what's around it, it's got to dissipate that energy. What's happening? How does this thing around it help the egg dissipate that same amount of energy? The device that you build doesn't take that energy away. It still has the kinetic energy, and it's got to get rid of it without breaking. Are you thinking about something? I'm hoping. What is the answer to the question? Now, I don't like it when teachers fish. They ask their audience a question, and they have an answer in mind. So I'm just going to tell you what my thinking is about it. But I also don't like to give you the answer right away. I like you to think about it a little bit. The answer is time. What the device does, it allows that energy from that reduction in kinetic energy to take place over maybe 1/4 of a second instead of 100th of a second. By doing that, it is able to slow down and stop. It still has to stop, but it takes a little extra time. So it still gets rid of that energy. The other issue of force is also involved here. So the point is, those wonderful activities, those classic activities, you can tie to science, and you can come up with entirely new ones, and in particular in the life sciences and in chemistry. Because I used to think, my mother wanted me to be an engineer when I grew up. And I said, no, I want to be a scientist. Because she said an engineer is someone who builds buildings. And I kind of like building buildings, but I love the stars. So I built telescopes. And I love designing the telescopes and the different ways a mount could keep that image really steady, you know. I spent hours and hours and hours doing that. And of course, that's engineering. Now I know that. And had I known a little bit about how to do that systematically, I built this portable telescope so I could take it to science fair projects. And when I built it, it was all wobbly. So I added this and that, and I thought, I can make it out of steel so it'll be strong. So I got these steel pipes. 300 pounds, my portable telescope. But I learned a lot from it. Okay, so let me move on a little bit. So that's teaching it as a core idea. So as a core idea, two, there are these three phases to it. So there's defining the problem, developing and testing solutions, and then optimizing. And the reason that we only chose these, if you look at a curriculum, it will identify, like engineering is elementary will have 5 different steps. Engineering in the Future has 8 steps. State of Massachusetts has 8 steps. There are 12-step programs, not just the usual program, but other 12-step programs in engineering. They all fit into these 3 phases, and when we came up with the NGSS, we did not want to limit anything, and we didn't want to choose one curriculum over another. So we came up with these 3 phases. They all fit. I'll show you a little later how they fit into Engineering the Future. But this idea that you have to define the problem, define and test solutions, and then optimize is the important part that you don't do in science. When science, when you got the answer, you move on. In engineering, you've got an answer that works, but is it the best answer? It's not necessarily the right answer, because there is no right answer. Is it the best answer? So you prioritize your different criteria, and then you do further tests to make it the best possible thing for what is most important in that case. It's a very different way of thinking. Okay, so the sweet spot is merging science inquiry and engineering design. How do we get there, and how do we choose the curricula to get there? I'm working on the NGSS. It's about 2 years ago. And I'm thinking at the time, these are the ideas that eventually made it into that NRC guide to implementing. I was one of about 6 people on that committee. And I'd been thinking about this for a long time. And I knew at the time a lot of curriculum materials that were developed that have, way back, that merge science and engineering. And of course, that's exactly what we try to do with Engineering the Future. But I knew there were other good curriculum materials out there too. And any teacher should have a chance to know about all those different materials. And I remember one time in particular, I think Stephen Pruitt was having an informational meeting for developers of all sorts, and a friend of mine, Gary Benenson, who developed City Technology, wonderful curriculum for elementary kids, was sitting in the audience, and he said to me, "I can't believe they're finally telling us about this. Why didn't I know about this before?" And I said, "But they are telling you, Gary. That's what this meeting's about. It's an informational meeting for you way in a year in advance of when it's released." And he said, "Yeah, but they're never going to know about my curriculum. We spent years working on it. I've got so many teachers that have implemented and tried things out and tested things. They're never going to know about it. They're going to start all new again." So it occurred to me, we really need to get the word out for all these different curriculum materials that exist. Now, when you go through the exhibit hall, if you see something that says aligned with NGSS, I won't say don't believe it, but take it with a grain of salt. Because it's too early. It takes years to really develop and refine a curriculum. Engineering the Future is not aligned with NGSS perfectly. It is, to a large extent, especially the spirit and especially tweaks that we're working on. Every curriculum developer is doing those tweaks today, and some are starting from scratch, starting from the ground. You should not be starting from scratch. There's good stuff out there. So when I got a call from Corwin Press, an editor, one of their acquisition editors from Corwin Press, "Do you have any ideas, Dr. Sneider, about what I can do?" First I tell them it's Cary. By the way, don't anyone call me Dr. Sneider. I'll worry I have to fix your bad back or something. It's Cary. So I said, "You know, I have a thought. I know about a lot of different curriculum materials. Teachers should know about them." And a while back when I was at the Museum of Science in Boston, we got a grant, we got a whole army of teachers to evaluate engineering curriculum. We put it online and we connected with all 50 state standards. Not many people used it because it was pretty boring. And boring doesn't help. Boring isn't very helpful to people when you've got so much work to do. So it occurred to me that let's have a book where the people who develop the curricula, who are really passionate about it, will write a chapter in this book. So they communicate And here's the most important part, what the kids do. There's nothing more important in whether a curriculum is good as what the kids do. When you look at a teacher guide, you'll find a dozen or 50 pages in the beginning of how it's aligned with this, how it's aligned with that, and what the scope and sequence is, and why this is just the best thing since sliced bread. Skip through that and look, and don't even look at the teacher guide. Get the student guide and go through it page by page until you get a really good feeling for what the kids do. That's what I was doing yesterday with the project-based inquiry science. We actually went through one of the units page by page and looked at the different lessons. It was a little tedious, so my apologies to those who bore with me on that. But you need to do that. But how do you decide which one? So the idea is that in a chapter of 10 or 15 pages, someone can really communicate what that's like. 40 different curricula rose to the surface. I only had about 2 people who wouldn't write a chapter who just didn't have time. But about 40 different curriculum materials rose to the surface, and we decided that nobody in the elementary level was going to pay for reading a chapter about high school, and vice versa. So we came up with a series of 3 books, and they were just out. All 3 of them are available now. And they're called The Go-To Guide for Engineering Curricula, grades K5, 6, 8, and 9, 12. So that's my little self-promotional plug. But it's here for a reason, because you should know what a variety of ones are. So I've asked them to write their chapters so that someone can read the first 2 pages and know enough about whether or not they want to read further. This is not a kind of page turner where you can't wait to read the whole next chapter and you read it from beginning to end. Nobody is going to read a book like this from beginning to end. What you're going to do is you're going to get a book that has good high school curricula or good middle school curricula and read the first couple of pages of each of those. It'll take you an hour. And then you're going to spend your time on the 2 or 3 that really matter. And when you read through those, then you'll know which ones you want to get to really apply the equip rubric to. Now, in some cases, I know I've heard a teacher tell me that their principal wants them to spend the summer writing curricula to implement the NGSS. Man, that's hard work. But if you can get some curricula that are pretty close, not perfect, but close, and you really like the approach, you're off and running. It can really help. And curriculum developers, this should be available for them. So this is consistent with the guidelines, all right? And I did disclose when I worked for the NRC that I had also worked for publishers and published things. You always have to disclose. There are always conflicts of interest, and the thing when you work for the NRC, you identify what your conflicts of interest are. And so that's one of them. I work for a number of publishers. Actually, I don't work for the publisher, but I develop things, and then publishers sometimes are willing to use them and sometimes not. So anyway, you might find these helpful. So now is time to talk about why did It's About Time allow me to talk about this here. And that's because 2 of the 40 chapters are about curricula that It's About Time publishes. One of them is project-based inquiry science. I did a session on that yesterday. That's middle school. And the other one is engineering the future. And I'm going to talk about that one now. Okay. Before I talk about that, I want you to have a short conversation at your table. So I'm going to stop talking for 5 minutes. And I want you to consider what are the 3 most important features you would look for to decide which curricula are worth time to review. So what are your values? And this is a chance to hear not just me, but other people at your table. By the way, if you're only sitting with people that you came with, I want you to change tables, because this is a really good chance. I love conferences when I have a chance to actually talk with other people. Otherwise, why go to a conference? And so come up. I'm going to ask each table to come up with a list of 3. So think also of who at your table will share those ideas. What 3 features will you look for in a curriculum to decide whether or not you want to apply the equip rubric? So if you get one of these books, or if you just go through the exhibit hall and you identify some curricula, how will you decide? What are your values? Any questions about the assignment? Pretty obvious, okay? Okay, 5 whole minutes. Go. Okay, ladies and gentlemen, let me have your attention, please. So I'm going to ask a report from each table. Stand up and give me the 3 most important features. And if there's something else that someone previously said, if it's a really important one, you can repeat it, okay? Because it's really important to hear if there are common ideas. Now, normally when we do this sort of thing, we say, I pass, if all the ideas have been mentioned. But I want to hear what they are. So, and if your table broke up into 2 conversations, I expect 2 reports. All right? So let's hear from this table first. Stand up and speak loud.
You said that it was important for a curriculum to be designed for the time it takes to go over. It must be engaging and connected to real-world experiences.
Good. Next table over here. Stand up, please.
Yes. You said it has to accommodate the different.
Face everybody.
It has to accommodate the different levels and the different abilities. And we also said it has to be. We also would like to have more activities to be more engaging, and so it connects the activities that connect the concept to with the students, so they can get that very easy. It has to be flexible. So that thing, and that's about it.
Good. So very engaging, accommodate different levels and abilities, students' abilities, and it's going to tie the science to the engineering and be flexible. Good. Next table. Stand up nice and loud, please.
We felt that we need to be, the problems would need to be open-ended, and that what's there would fit our style that we already have. We don't have to throw the baby out with the bathwater, so to speak. And then we have some ease of implementation, so we don't have to reinvent the wheel.
Good, good. And that open-ended means so it's creative. So kids can be creative.
More creative.
More creative, okay. Back table.
A lot of similarities. Really coming up with as many creative and interesting and original ideas that we're engineering and into the core content that we already have. Also examples of how you can apply cross-cutting components to those, and also how they align to explicitly how they align to.
Good. The cross-cutting concepts is a really important idea, which we haven't talked about. Table next to them, please.
We felt that they really needed to connect with content, that support content that we know we already teach, that it would have an alignment factor, and that it would certainly be related to something that we value in our program.
Okay, good. The table close next to them that's closer to me. Go ahead. All right.
We felt it should be something that the teacher is passionate about, not just forced on the instructor, because that's the initiative that's taking hold. We wanted something, or we'd like to see something that allows students to be able to put things into practice, and something that does integrate very easily with the curriculum or the models that we're using.
Good. I just want to emphasize that first one about passion. When you look through, to choosing curricula, trust your gut. If it's something you like, you're going to be more likely to actually like teaching it. So it's something to think about. It's not always a mechanical process. Start with this table next.
Well, first of all, we basically came up with maybe 3.5.
It's okay.
We started out looking at engagement, and then we looked at interactions between the students and all that. We put that together as one, call it engagement and interactions. Connections to content, we have a lot of different content areas that we have to look at, so you're going to have to look at individual programs for connections to content. And then we went to marketing cost.
Good. Good. Thank you. Some good new ones. Next table.
We talked about real-world applicability for students, explicitness in the alignment to practices and cross-cutting concepts, and interconnectedness in terms of bundling multiple disciplinary core ideas and being transdisciplinary and cross-academic subjects.
Very good. Good. Esther Hopkins' table back there.
Really, we talked about some of the exact same ones, real world and
problem-based issues that students can really connect with, and meeting content objectives, but also the three-dimensional aspect that we want to incorporate to NGSS. And probably our new one is just a greater focus on differentiation. And as I was listening to just everybody share about where they're from, just addressing all the needs of diverse learners in that. So, looking to Appendix D and making sure that the curriculum that we choose is going to be applicable to all of those kids that we're teaching.
My boss always said, the easy part is doing formative evaluation or formative assessment. The hard part is knowing what to do about it. So differentiating learning is the hard part. Okay, and our last table over here.
One of the things that we had was, is it at the right level for our students, and is it going to prepare them for the next level?
Yeah.
Also, we want to be student-centered. We want them to work harder than we're going to work in the classroom and make sure that they're getting the benefit. And then also that the activities that are there, the resources are meaningful, they're aligned, and have they been used? Has anybody done them, and are they effective? If we look at something and we don't have a good report on it in terms of I've done this and it's effective, there's no point looking at it.
Good. Okay, those are excellent. I'm not going to be able to address all of those features, but you need to address them. So when you decide what you're going to evaluate, it's really good to start with that list. And you may come across other things you hadn't thought of when you look at other curricula. But know what you're looking for. Make that list for yourself before you make some decisions. And don't necessarily buy a new curriculum yet. You might can get some supplementary materials. I know I shouldn't be saying this doing an exhibitor workshop, right? But you really want to be sure you know what you're getting and what it's valuable. And frankly, this particular company, that is what the people care about, that you have what you need to do a good job, or I wouldn't be standing here. So let me quickly go through and tell you a little bit about the Engineering the Future curriculum. It's called, the subtitle is Science, Technology, and the Design Process, which says we try to bring them together. Developed before the framework, but nonetheless anticipated, like all the other curriculum materials in the books I told you about earlier. So it's designed for students in grade 9 or 10, algebra level, simple algebra level. Has been adapted for some schools in grade 8, but I think it works better in probably grade 9 or 10. And one of the main goals is to expose students to a wide range of different careers. There are 4 projects that carry throughout the year. So that provides the continuity. And the most important thing is what the kids actually do. So they're really engaged in doing engineering design through the whole thing. But they also have this reader with chapters by a number of different engineers. As you can see, I like people who write chapters about what they do. And if they write about what they do, it's really meaningful and engaging. And you really see their passion come through. It's not only engineers, by the way, they're also city planners and graduate students and so forth. There's some amazing people that work in developing countries and help people work for Habitat for Humanity and so forth and so on. The engineering that would really get kids turned on and excited and say, hey, maybe I want to do this. Not that the goal is to get them to be engineers, but to get them to understand the nature of engineering and why it's exciting. And then, of course, there's a teacher guide. So those are what the materials are. So quick, what are the four units? So the first one is Design an Organizer, and it begins with a quick build. Design a cell phone, or what do we call these, personal assistants now, personal digital assistants. Design a holder for it. Because everybody just about has one, or they know someone who has them, and they know the problems with it. So they share those problems, they define the criteria and the constraints. We give them some cardboard and they make one. They make us a holder for it. And then they show off their ideas and they market them, and it's a lot of fun, but they didn't stop and really analyze what's needed, what the biggest market would be. They didn't look at 3 or 4 different solutions. So then we show them a video about how engineers do this, which is very different and takes more time, and involves identifying the criteria, prioritizing them, recognizing their constraints, and developing a decision matrix to figure out which is the best solution to develop and test. Because developing and testing takes a lot of time and energy. You can't develop and test every idea that comes up. So it's a real, the main project that they then apply to is to design an organizer for something they care about. It could be sports equipment, or it could be cosmetics. So it gets the kids involved in using design about something they care about. Now, when I first heard this idea, I said, an organizer? That's an exciting project? Turns out the kids really love doing that because they're doing something for something they care about. And the idea of an organizer pervades our society. What is a building but an organizer for different functions? What is a city but a way of organizing all the different buildings? And it's got inflows and outflows. So organizer actually turns out to be a really interesting project. We also introduce, this is Amy Smith, who's a instructor at MIT, who brings her kids to developing countries to develop sustainable products. And this is Jamie Drulard, who's an aeronautical engineer. So we have a lot of different people. They authored chapters in our book for the kids to read. And Jamie defines the engineering design process. This is the 8-step version, and here it shows how it fits the 3-phase versions from the NGSS. So they're really the same, except this is a high school version. It's a little more specific. The second one is to design a building of the future. And here we look at big ideas about new urbanism. What are our cities like? How do they serve human beings and humans' needs? And then how can we design a building that would fit into a new kind of city that really minimizes the amount that we have to spend, minimizes our carbon footprint, for example. This one also introduces structures, materials, and energy flow. For any building, you really have to think about how you're going to use insulation. And in different parts of the country, you need different types of structures to build a more sustainable building. The third one, Project 3, is really about building this little putt-putt boat. It's a weird little thing, and it's with one little candle. You light the candle in it, and it goes putt-putt-putt-putt-putt-putt around. I recommend you go to the Engineering the Future website, click on the video, and you'll see a really interesting video about kids trying to figure out how it works before they build it themselves. And then building it is not an easy job. It takes some fabrication work. And then the work of it is to improve the design of the boat so it performs better so it can be patented. And they look at the first patent, and the job is to try to improve the patent. So it's a lot about the patent process. And we hear Amy Smith's ideas about patenting, different points of view about patenting. And then once they think they know how it works, they have to argue from evidence to support this idea or that. That's the inquiry process leading to the design process. It's a beautiful marriage of the two. And then they design and they test their solutions. And they see how well it does perform. Sometimes it does, sometimes it doesn't. But it's the process of doing it, of course, that's so exciting. If it even works, it's exciting. They all work eventually. And then the last one is about electricity and communications, where they build circuits for scoreboards. They build a little binary function to display numbers. It's always interesting to me how simple ideas about circuits allow you to display different binary numbers. And different science concepts that are displayed throughout the entire course. The concept of energy. That energy always flows from high energy concentration place into a low energy. That might be from hot to cold, from high pressure to low pressure, or from high electrical potential to low. And when that is equalized, the flow will stop. So as long as there's a difference, energy will flow. And also, the rate of flow is inversely proportional to the resistance. That idea applies if you're talking about electrical resistance, or if you're talking about thermal insulation, which provides resistance to energy flow. The idea is to understand energy not just in one context, but in at least 3 different contexts, and understand how that energy flow powers our whole civilization, helps cars move, helps power the lights in this room, and so on and so forth. So it is a deep dive into a few concepts, not all the concepts. The focus here is on engineering as a course, not just on the science in this case. And we've got 2 minutes for one question, and then I'll be around to answer other questions. I'll be hanging out here for a little while. Yes?
I was wondering, one of the NGSS standards talks about modeling, and when modeling, but they seem to express computer modeling, and I was wondering how that's built into that.
We did not, yeah, that's a good question. In the very first chapter, the very first project, we have a section on engineering design, and engineering drawing, rather. The best way to learn engineering drawing is through a CAD program. Well, you do it by hand first, and you knew the difference between orthographic and perspective and oblique drawings. Orthographic is the most common, most used, the top view, the side view, the front view, and so forth. And so we encourage CAD, but at that time when we developed this 8 years ago, not as many schools had the capacity. More schools have the capacity now. So now it's going to, when we do this again, CAD will become a part of it. But the later parts too, involving simulation, also needs to be built in. At the time, we did not want that to be the barrier, because there were other curricula out there that really insisted not only in having computers, but particular computers and particular software, and they were very expensive. We wanted all students to be able to use this material. So we will be, in time, as we're improving it to be more consistent with the NGSS, be adding more computing capabilities, more software, more recommended simulation programs. So, good question for the last one. Thank you, everybody, for coming. I really appreciate your being here. Come on up if you have more questions.